Welcome to an interactive course designed to validate and improve our knowledge of heat treatment. The topic of this course is to explain the iron-carbon diagram. The iron-carbon or iron carbide Fe3C diagram is a fundamental source of information for understanding the heat treatment of steels. Iron as an element is very rare in its natural state, and usually contains a certain amount of carbon or other alloys that are added to the steel to change its mechanical properties. However, the resulting properties of the steel are determined by the concentration of carbon. This diagram describes a binary system in which phase and structural transformations in iron can be read as a function of the amount of carbon and temperature. At the point 0%, there is 100% iron. Depending on the form of carbon expelling, we distinguish two basic types of equilibrium diagrams. If carbon is deposited as a metastable iron phase in the form of iron carbide Fe3C, we are talking of an equilibrium diagram of metastable iron and iron carbide. In this case, the amount of carbon in mass percent contained in the Fe3C phase is plotted on the horizontal axis. If the carbon is released in the form of graphite, then we are talking about a stable iron-carbon equilibrium diagram, and the horizontal axis will represent the net carbon content in graphite, also in weight percent. Since the metastable diagram comes into consideration for carbon concentrations up to 2.1%, then it is usually applied to steels. For a higher carbon content above 2.1%, for the area of cast iron, a stable iron-carbon equilibrium diagram is usually used. However, since we will continue to deal with heat treatment, the diagram of the metastable binary system Fe3C will be crucial for our needs. If we look at the diagram, the upper line marked in red means the so-called liquidus. It is the line above which iron is always in a liquid state. This line is important for iron production. Below this liquidus line, various solid phases of iron begin to precipitate with decreasing temperature, always depending on the carbon content and/or other alloying elements. The lowest liquidus temperature is 1147 Celsius and is valid for a carbon concentration of 4.3%. The green-marked curve is the solidus line. This is the interface where iron below this curve is always in a solid state. As already mentioned, the percentage range of carbon for steels lies in the range of 0 to 2.1% carbon. For a better understanding of the problems associated with phase transformations of steels, it is necessary to clarify some basic concepts. Below the green solidus curve is the austenite area. At the lowest point of the austenite area lies the so-called eutectoid point, which divides the steel region roughly into two halves. The eutectoid point corresponds to a carbon concentration of 0.8% at a temperature of 727 C. In the range of carbon from 0.022% to 0.8%, there are so-called hypoeutectoid steels, in the range above 0.8% to 2.1%. There are hypereutectoid steels. The solidification of hypoeutectoid steels passes through the curve with temperature A3, where a ferritic-perlitic structure is precipitated from austenite. The solidification of eutectoid steels passes through the eutectoid point, and in this unique case, the austenite changes to 100% perlite. The solidification of hypereutectoid steels passes through the transformation curve ACM, when the structure changes to a structure of perlite and secondary cementite. The area to the right of the 2.1% carbon concentration belongs to cast irons, but it is necessary to mention it briefly. During the solidification of cast irons, crystallization passes through the solidus line, also called the eutectic. At a carbon concentration of 4.3%, the lowest melting temperature of 1147 C is reached. At this point, a eutectic called ledeburite is formed, which is a mixture of austenite and cementite crystals at temperatures above A1, or pearlite and cementite crystals below A1, the so-called transformed ledeburite. At the maximum carbon concentration in steel, with content of 2.14%, this ledeburite structure also begins to appear in steels and is characteristic mainly for some tool steels such as 1.2080 or 12379. It forms the so-called group of ledeburite tool steels with 12% of chromium. As already mentioned, the eutectoid line is the line where the eutectoid, the so-called pearlite, is formed. It is not actually a single phase, but a combination of two phases in the form of ferrite and cementite lamellas. The amount of pearlite in the structure varies according to the carbon content. The pure pearlitic structure has 88% ferrite and 12% cementite. The area of formation of pure ferrite is completely minor in steel, because the solubility of carbon in iron in ferrite is very low. It is only 0.022% carbon. Therefore, the structure of sub-eutectoid steels is always made up of a mixture of pearlite and ferrite. In super-eutectoid steels, the structure consists of pearlite, as in the previous case, and so-called secondary cementite, expelled below the segregation temperature ACM. Iron is characterized by the fact that it changes its structural lattice during heating and cooling. Depending on the temperature range in which iron is found, two basic phases can be defined. The first is ferrite, an interstitial solid solution of carbon in iron alpha. It is a lattice where there are 8 iron atoms in the corners of the cube and then 1 carbon atom in the middle. This lattice structure means that the solubility of carbon in ferrite is very low. This low solubility means that steels with a higher carbon content form a mixture of ferrite and pearlite or secondary cementite during solidification, where the carbon is deposited. However, this is only valid when the melt cools slowly. In the case of rapid cooling, during quenching, the carbon cannot change position by means of diffusion processes and remains in the alpha iron lattice as a highly supersaturated solid solution. Martensite is with high hardness, but also fragility is formed. The second basic phase is austenite. Austenite is only found in carbon steels at high temperatures. Because its lattice is cubic, face-centered, its ability to hold carbon is far greater than that of ferrite. The lattice has 8 iron atoms and 6 carbon atoms. The maximum solubility of carbon in austenite is 2.18% at a temperature of 1147 Celsius. That is almost 100 times more than ferrite. In the area above 1394 Celsius, the so-called delta ferrite is also found. However, its presence in the structure at room temperature is rather exceptional. The basic principle of heat treatment is the change of the crystal lattice. Knowledge of transformation processes and their understanding allow us to perform quenching from the correct austenitic temperature, perform annealing processes without or with recrystallization or carburizing. One of the most important components of the phase states of iron is austenite. However, the austenite area is very diverse and depends significantly not only on the amount of carbon, but also on other alloying elements. Therefore, for each type of steel, depending on its chemical composition, the austenite region will vary slightly, just as the equilibrium phase diagrams of these different steels will also differ. To further understand these phenomena, it is necessary to remember that the equilibrium diagram shows the behavior of steels during slow heating or cooling processes, with sufficient time for the transformation to occur. However, the situation will be different during rapid heating, especially during rapid cooling. This figure clearly shows what possible structures can be achieved with one steel with a defined amount of carbon. If steel with structural components such as ferrite, pearlite, or cementite is heated to an area of austenite and then slowly cooled, all processes are reversible, and after cooling, all the original structures will be present in the steel, even if in a slightly different form. But if we cool quickly, there will not be enough time for carbon diffusion, and various types of supersaturated phases will be created. As we have already stated, austenite has a much greater ability to absorb carbon, and therefore, when steel is transformed into austenite, it is dissolved from the pearlite or cementite phase to austenite. On the other hand, if we prevent this process by rapid cooling, there will be no reverse transformation to the phases according to the iron-iron carbide diagram, but supersaturated solid solutions of carbon in alpha iron will be formed. These are called martensite or bainite. Unfortunately, nothing is as simple as it looks. All of the above applies only to the iron-carbon system. However, as soon as we start alloying steel to achieve special properties such as hardness, toughness, abrasion resistance, corrosion resistance, etc., then the alloying elements fundamentally change the FEC diagram. Some shift the conversion temperature A3, others ACM, others A1, or the position of the eutectoid point. This complicates the situation because, as a result, we need a separate and unique diagram for each steel separately. Now let's look at these structures in detail. You can click on the icons one by one. The phase transformation of steel is usually shown on the so-called CCT diagram. The abbreviation CCT stands for Continuous Cooling Transformation. At different cooling rates, transformation curves for martensite, bainite, pearlite, and carbides and other phases in steel are analyzed. The user, especially the technologist, is able to determine from the diagram both the necessary temperatures for austenitization and the necessary cooling rate of the steel to achieve the desired structure or to achieve the required hardness. It is therefore a basic document for technologists to determine heat treatment parameters. The CCT diagram is prepared for each steel individually and clearly shows the phase transformations in steel according to its alloying and the amount of carbon. So, it's an image of our iron-iron carbide binary diagram, but it takes into account both the chemical composition of the steel and the cooling rate. In connection with transformation changes in steel during heating and cooling, it is necessary to mention one more problem. The change of the crystal lattice is accompanied by a change in volume. Since all phases are in the solid state, these transformations can be accompanied by high compressive or tensile stresses. This figure shows the dilatometric curve for changes in the dimensions of the crystal lattice of iron due to both temperature changes and transformations to another phase. In terms of volume, untempered martensite has the largest volume, followed by tempered martensite, bainite, pearlite, and ferrite. The smallest volume is occupied by austenite. In the case of quenching steel, when reaching the martensite start temperature, this change in volume is so significant that it can be the reason for the formation of high tensile stresses and subsequently cracks during quenching. The iron-carbon diagram course is over. It covers my many years of experience and practice, but it is clear that the issues can be very complex and extensive, and may not exactly match your experience. If you have any comments or suggestions for improving the course, please send them to the contact listed. My goal is for the courses to provide essential information for heat treatment employees at all levels so that they can continuously improve. The level of content is therefore adapted to allow both existing employees and new employees who do not have knowledge in the field to take part in this course. Based on these comments, I will improve and expand the courses so that they are a real benefit to everyone. As you have probably noticed, the course was led by me, but the Great Speech Generator 11 Labs. Thanks to him, my English will also be understandable. So thank you also to Bill and his voice for his contribution to the field of heat treatment. What you saw as a video on YouTube is just a picture of what is created in Adobe Captivate as an e-learning course. It is available on my website, jstconsultancy.cz. You can access it for €20 for 1 week, €40 for 1 month, or €60 for 1 year. The course is created in HTML5 format. However, it can also be exported to ASCORM 1.2 format, which stands for Shareable Content Object Reference Model. Other formats are possible for different LMS systems. You can order this form at my email address, and you will receive the complete course in HTML5 code and a permanent license for €500 per course. The compressed zip file will be 50-200 megabytes in size, depending on the content of the course. You can then install this file in your corporate cloud or in Moodle LMS 5.0 on SharePoint or in the HR module of your ERP system, such as SAP, which can communicate with a learning management system that meets the LMS specification. In this case, you will be able to prepare a training plan for each employee, including an evaluation of its implementation and success rate. Each course contains a test with many questions, and the output is a certificate of successful completion of the course. You can archive these certificates and use them for employee motivational rewards. The advantages of e-learning are obvious. The employee does not have to go anywhere. They can complete the course anywhere, on a computer, tablet, or even a phone, at work, on vacation, at home, and you will be sure that they have the necessary knowledge to understand what is happening in the heat treatment operation. I do not know of any disadvantages, so I just hope that these courses will serve you and be useful to you. And what is my vision for the future? You can see this in this process map. So far, 16 have been created in Czech and English, and I will gradually add new ones, depending on their importance in the life of the heat treatment operation. I don't know if the courses are perfect, but I'm sure it's a promising form of education that we shouldn't ignore.